Welcome back. Let's go ahead and finish up chapter 10. So far we've looked at the TTT diagram, and we've talked about coarse perlite, fine perlite, bainite, and martensite. And I mentioned tempered martensite, and we're going to go ahead and look at that a little bit closer now. So here is our time versus temperature profile for the processing. This looks a lot like precipitation strengthening. And so what we have here is we're going to start off at some T1, say room temperature. We're going to go ahead and heat up our steel so that we austenitize it. That's our first step in all these processes. So we form a complete austenite structure. We undergo a quench back down to room temperature, and we know from the TTT that this is going to form martensite. Now, I said martensite is very strong, it's very hard, but the problem is that it's too brittle to use in that particular form. So then what we're going to do is we're going to reheat that for just a few hours, maybe just an hour, a few hours, maybe up at 300, 400, 500 degrees C. And we're going to heat it, we're going to hold, and while we're holding, since we are from the phase diagram, right, we're going in that ferrite cementite phase region, we now have enough diffusion that since we've increased the temperature, that the martensite no longer will be frozen in, but will actually form the ferrite and cementite from our equilibrium diagram. And so we're now going to get ferrite and cementite to form, and then we'll cool back down to room temperature. So we're going to take a look at the structure of this because it's going to be quite different in shape. So far, to get this ferrite cementite for the eutectoid composition steel, we had to come through the liquid region, and then we came into the ferrite cementite, right? And in this case, this was perlite. So this was our eutectoid phase. But now we're getting this ferrite cementite mixture from martensite, a solid, not from a liquid. And so we expect to have a very different structure, not a layered structure anymore like we had in the perlite case. And in fact, what we get for tempered martensite, what it looks like is a matrix of ferrite with cementite particles all throughout. So this looks again like a composite material, but now we've got very small precipitates of cementite in this overall ferrite, which is a more ductile matrix. Okay, so this brings back a lot of ductility to this material, but these cementite particles are extremely fine, and so they resist the movement of dislocations through this structure because there's so many particles, there's so many impediments to trying to move dislocations throughout. And you can see all of the different length scales that are in this ferrite structure. All right, I got a note here that this looks a lot like spherodite. We haven't touched on that one yet. I'm going to do that in a minute. In spherodite, you'll see it looks a lot like this structure, except spherodite is going to have a much, much bigger scale. It looks like a very highly coarsened martensite, tempered martensite. So this tempered martensite has ductility, but it still retains a lot of the strength of the martensite. So we could go ahead for a particular steel, and we could plot out the tensile or yield strengths versus the tempering temperature. And in this particular case, these were all done for a 1 hour temper. And so we can see that at the lowest value is of tempering temperature, like 200 degrees C. We have some very high tensile and yield strengths and reasonable ductilities. That's not a bad ductility at 40% reduction in area. It's not bad at all. And then as we would increase that tempering temperature, again, these are all just data sets that are done at 1 hour, so 500 degrees C for 1 hour. You can see we're getting this fall off in the tensile and yield strengths, but we're getting very large increases here in the ductility measure. So again, a trade-off, what strength we need and what ductility we need. But all of these strength values here are much, much higher than what we get in the other microconstituents of the steel, and we'll take a look at that summary slide coming up. So far, if we take a look at the hardness, and remember this is correlated to tensile strength and yield strength, and we take a look at that as a function of the percent of carbon in our material. So far, we've only been talking about 0.76, which is the eutectoid composition values. So something like this. And we're all going to look at this also as a function of the microconstituent. And so we have a coarse pearlite and a fine pearlite. You can see the finer structure of the pearlite. The more layers we have, the closer the layers are together, the more resistant to dislocation motion, and the higher the strengths. And then spheroidite, again, we're going to do that in a minute, is going to be the weakest of the structures and very high ductility. So spheroidite might be useful for forming the material into a different shape, but it's not very useful in itself because it's too weak, and so you then have to reprocess to form a new microstructure. All right, so the question is, where does tempered martensite fall in this plot? Okay, so we're going from coarse martensite to fine martensite, and then we're going to see, where in this plot is tempered martensite. The other thing we notice on this plot is that as the carbon content of any particular microstructure increases, so does the strength. Right? So weight percent carbon goes up, so does our tensile strengths, yield strengths, etc. They also rise. All right, and hopefully that makes sense from the phase diagram. If you think about doing a phase fraction calculation, you'll see the more carbon you put in, the more cementite that you'll have in the structure, and so we expect to have these higher strengths. All right, so fine pearlite was the highest curve on that last plot, so here it is again replotted. But now you can see the martensite, you can see the tremendous increase in the hardness. Again, that also means tensile and yield strengths. And then if we temper it, then we're going to get some value between these two. So this is showing one case for 371 degrees C, tempered martensite. So the tempering is always going to be higher than the fine pearlite. And again, the advantage is that we get back now the ductility. Again, where the martensite is just too brittle to use. So we have quite a bit of range here that we can tailor now the mechanical properties of the steel, all the way from spheroidite on the lowest end, all the way up to martensite on the highest end. All right, so let's just ask the question of what happens if we take a pearlite structure and we were to hold that at a high temperature for some time. So remember, this pearlite structure forms because of kinetics. When we form this layered structure so that we can keep up with the diffusion and be able to part the compositions, because the carbon is very high in these black layers that are the cementite, and quite low in the whiter areas, which are the ferrite. And so this is a kinetic case. But this particular material, as pearlite, really has a fairly high energy because it has a lot of phase boundaries. And all these phase boundaries are defects. So if we were to heat this up or maintain it at a high temperature and keep holding, then diffusion would start kicking in, and we would eventually start breaking up the layers, as you can see going on here. We'd start widening the layers, and the longer and longer this continues, we would eventually break up all these layers and form spheres of cementite. The reason we want to go to spheres is because spheres have the smallest surface area, so in this case meaning phase boundary area, relative to the volume. And so if we can break the structure up, coarsen it, eventually get it into spheres, then we're helping to reduce the energy of the phase boundary area in the structure. Now note that when we do this, this weight fraction of the phases is not changing. So we're not increasing the amount of the cementite or the ferrite. We're simply changing it from layers into spheres. The weight fraction comes from the analysis of the phase diagram. That's the equilibrium values that we are looking for in terms of the phase fractions. So if we keep holding, so maybe this is 24 hours, 48 hours, maybe 3 days, depending on the temperature, we will eventually break that perlite up completely, and we end up with these spherical particles. And I know these aren't perfectly spheres, but we refer to them as spherical particles. And so this is referred to as spheroidite. Now this looks a lot like the tempered martensite that we just looked at, except that the length scales, I don't have a bar on this one, sorry, but if you take a look in your textbook when you're reading, take a look at the magnifications, and you'll see that this spheroidite is on a much bigger scale than the tempered martensite. And so here the dislocations, the separations between these is much larger, and so this does behave as a very soft, weaker material, but very high ductility. Again, these particles here are the cementite, and then this is the matrix of ferrite. And the weight fractions, again, do not change. And the longer that we hold at this elevated temperature, the larger these particles become. So ultimately, the system would be happy if there was just one big cementite particle, because that would minimize the surface area of the particle relative to the volume that it contains. Of course, as the particles get bigger and bigger, then the increase in their size starts to become slower and slower as the diffusion paths between particles increases. All right, so let's get a summary then. This is finally all of the microconstituents or structures that we have for the steels that at least we're going to be concerned about in this course. And on this chart here, 10.2, they're listed in their order from the weakest to the strongest, highest strength structure. And so spheroidite, right, is again the weakest of them all, then followed by coarse pearlite, fine pearlite, bainite, tempered martensite, and then martensite. Okay. And then these are also listed, if you want, in terms of decreasing ductility. So the spheroidite is very soft and ductile, all the way down to the martensite, which is very brittle. And then we just have a description of each of these structures. Notice, though, the phase diagram tells us that ferrite and cementite is what we need in the final structure. So all of these structures here contain ferrite and cementite. This is what we expect from the phase diagram. The difference is that the kinetics are kicking in and saying something about how the cementite and ferrite look in terms of, are they spheres, what is their spacing, are they layers, are they needles, and all of that is affecting our mechanical behavior. And martensite, we said, was a non-equilibrium structure, so that's why it doesn't show up in the phase diagram. And we only got this because we froze the austenite structure in essentially as we dropped to room temperature. We don't have enough diffusion to actually move carbon around to form the ferrite and cementite. So instead, because of all the strain, the system just distorts into a body-centered tetragonal structure rather than the original face-centered structure of the austenite. Okay, so what I wanted to show you with this, we've used the TTT diagram before, but what I just wanted to show you is that, you know, the TTT diagram is kind of a given, and if you walk down the TTT diagram, you'll basically be walking straight down this list. And so it's an easy way to remember the soft, ductile, weak spheroidite all the way up to the very hard but brittle martensite. And so spheroidite is anything at a high temperature held for a long time. So this is spheroidite. We said that the upper portion in this is coarse pearlite, and then went down towards this end is fine pearlite. Then this is our bainite region. We quench all the way down into martensite, and then if we were to reheat martensite at some temperature in here, we would end up with tempered martensite. So thinking of it that way, they're all listed exactly like this table. So the weakest, most ductile up here, and the most brittle, most hard highest strength martensite down here. So just a way to think about it. So each of these structures as I move down this way are getting finer and finer in scale, therefore harder and stronger, but less ductile. All right, so the other thing we want to point out is that we said that austenite is how we get to, let's say, coarse pearlite. That's how we would get fine pearlite, bainite, and that's how we would get martensite. I can't go from coarse pearlite to any of these other structures, nor fine pearlite to any of these other structures. So if I want these, I have to go from austenite. And then from martensite, I could get tempered martensite. Okay, so first I'd have to go austenite, I'd have to get my martensite, and then I could reheat and get my tempered martensite. So maybe I'll actually, let me just write it off of here. So tempered martensite. So that's the only way I can get to tempered martensite is that path. Nothing else will convert into tempered martensite. So this is my one path. This is the only way to get these structures. Now spherodite is the exception in that all the structures, doesn't matter what I have, they can all transform into spherodite by simply holding at a high temperature for a long time. So long time meaning days. So everything can go to spherodite. So what would happen if I started off with austenite and then held at a long temperature for a long time? What I'd end up getting would be I'd go from austenite and then I'd probably go to a coarse pearlite, depending on how high the temperature was, or maybe a fine pearlite, and then continuing the hold eventually transforms into this spherodite. Okay, so those are our rules in terms of what kinds of structures we can get. So the CCT curve diagrams are, I think, are relatively straightforward to use, so I'll let you read about them. There's a few slides in this that you can take a look at, but essentially the main idea with those is if you, the CCT diagram, this is the CCT diagram. The CCT diagram basically says that you can only get pearlite and martensite from a eutectoid composition. And we're not going to worry about the off eutectoid composition steels, 0.76, I'm not sure why it's 79, 0.76 weight percent. So we're not going to worry about the ones that have other additions in them or the off eutectoid compositions like hypo or hyper eutectoids. We're just going to stick with the eutectoid for purposes of this class. The other charts, some of them are in the text and you can read about those, but don't worry too much about it. I'm not going to ask you any test questions on them. So the main idea with the CCT is basically if you know what your continuous cooling rate is, we've got some critical numbers. So if you are faster than 140, then you're going to be over this part of the diagram and you're always going to have martensite. And if you're between 35 and 40 degrees C per second, you're going to have a combination of the two, martensite pearlite, and then anything less than 35 is just your pearlite. Okay. And I won't ask you for whether it's fine pearlite or coarse pearlite, but you can imagine that the closer you are to this sort of 35 number, you can expect fine pearlite, and the further you are, where's my curve, further you are out here, you're going to be with a coarse pearlite. All right, but those are really the only numbers you need, and you don't have to write down for the martensite pearlite. You don't need to say how much fractional amounts there are. It's just martensite and pearlite. So those are pretty straightforward. All right, so for example, if we had a 1 degree C per second case, okay, that's going to be out here somewhere. That would be a coarse pearlite. 20 degrees C per second would be closer in here. That's going to end up being a fine pearlite. Unless asked, you can just write pearlite. 50 degrees C is in between, so that's going to be a martensite plus pearlite. And then, of course, 175 is just going to be martensite. Write that down, coarse pearlite. fine pearlite. Okay. All right, I think that is it for chapter 10. And I will talk to you again, I guess, when we get into chapter 11.